I think almost all of you by now know Dr. Wagner, but let me now say a few words. It's my privilege to reintroduce Dr. Wagner to you. He, like I mentioned last time, is a multifaceted personality. He's a licensed master builder. He's a government counselor. He's a chartered expert at court. He's been a consultant at the World Bank for more than 15 years. He's an international consultant for the underground structures. He's got, ladies and gentlemen, he's got 40 years plus experience in tunnel design, construction, and consultancy. He's also been teaching as an assistant professor in the Graz University, Austria. Those of you who are aware, this is one of the most renowned university in the world. He's been a vice president in the ITA and also an expert member on the EXO Council, Executive Council of the ITA. I can go on to speak, but I will only say this much this time. Next time I will find a research and find some more details, interesting details about him. But I think it is his commitment, his passion for this particular field of tunneling and underground space. Just see the kind of knowledge that he has, and he wants to share his knowledge and experiences with all of us. A little bit about the subject matter of the day. You know that it is there. That today he's going to be speaking. Professor is going to be speaking to us on the geotechnical characterization of soil and rock. And you're aware that the geotech characteristics and classification aim to determine the ground characteristics by assigning certain values to a set of parameters. We are aware that rock mass is a matrix consisting of rock material and rock discontinuities. Deformities, discontinuities are the one which throw a challenge on the geotech aspects. Fractures control the mechanical response of rock masses. I think it's a very loaded statement which has been said. And he is going to be speaking to us more and more about this subject matter. So without getting into his domain, I will now hand you over to speaker for the day. So Dr. Wagner, all yours. We are delighted to be with you today and again would get enlightened on this very complex subject, yet very important subject in the world of tunneling. So over to you, sir.
Thank you very much for this kind introduction. Again, I feel deeply, deeply grateful for the fact that I have been introduced by you. And let me just add a few sentences on what you said about India and tunneling in India and about the efforts and the intentions of India to host the WTC, one of the next World Tunnel Congresses. Since the WTC in Dubrovnik, I have been always very supportive for the Indian Tunneling Association, for the Tunneling Association of India. And I continue to do that, and I will use all of my power and all of my influence to support India to get what it really, what it should get. India should get the WTC in one of the next, which we don't know, one of the next events of the World Tunnel Congress right now. As you may have heard that the Kuala Lumpur Congress WTC 2020 has been virtually held, and WTC 2021 has been postponed from 21 to 22 in Denmark, in Copenhagen. So maybe we can meet again as ITA in Copenhagen, not virtually but real. I believe that there is an end to this Corona story. Sometimes, I hope next year, maybe by the middle of the year, maybe by the end of the year. But I think we will, and we have shown as a human society that we are able to control such pandemic diseases which we are confronted and faced right now. But India really, because of the fact that there is so much going on in tunneling and underground construction. So India has a lot to show to the world what it can do. There are some outstanding projects like Metro Delhi. There are some outstanding projects in hydropower, tunnel construction also. So India really can show to the world that it is having most capable engineers and most capable authorities to manage these projects. So I can assure you that I will do everything to give support to India for the next intentioned WTC. And I very much look forward to that. Now with that, I would like to switch over to...
Yeah, and thank you for that, Dr. Wagner. We know that you are a supporter, and not only here, you have been a supporter at the International Fora also, and we know that you're very keen that sooner than later, India should get a chance to host a WTC, and the worldwide. Now we are aware that one of the strongest proponents in the world of tunneling, and not only tunneling, I would say underground space, is India. This is where the entire world industry, the world academia, the world experts are now looking at. And for that reason, I think there's every possibility that India should get a chance to showcase its skill, its industry, and what the future holds for the experts and for the equipment suppliers and for the builders in the field of tunneling. Thank you for supporting us. And at least that thought is great, that you always feel that it's our turn. It's high time that India gets the turn. Thank you.
It is my deep honor and it is my deep pleasure to do whatever I can for India with all of my influences and my lobbying power, you know. So I will for sure do that with lots of conviction and with lots of enthusiasm also. So thank you very much. But for today, I would like to, maybe we can switch to the next slide because it's a little bit different than the slides before, as it shows, it gives an overview, but there was, yes, this shows the training program which we are going to have today and in the first 4 months of the year 2021. So today we have geotechnical characterization, and we will have an excursion, a little bit excursion into history also, because one of the founders of geotechnical engineering was Karl von Terzagli, which was an Austrian engineer. Actually, he was a alumni or a graduate from Technical University in Graz. And he ended up on the Massachusetts Institute of Technology in Boston in the United States. And he has a lot of very, very interesting curriculum in between. So we are also going to, in January, February, March, and April, to have lectures on layout of caverns and with an emphasis on shotcrete. I really like to bring to the table everything I know about shotcrete, because shotcrete is such a key material and technology also for our underground construction industry. And with that also, I will talk in February on NATM and TBM design guidelines. NATM for New Austrian tunneling method and TBM for tunnel boring machine. So with regard to that, we will talk in February also about very actual development on the market. And that is, just to name it as it is, that is Elon Musk and the Boring Company, because he thinks he can build tunnels at 10% of the cost of what we have today. So whatever that is and whatever that may include, we will talk about that in February. And in March, I was thinking to talk about contracting practices, contracting models, and also there will be some repetition on aspects of risk management in March. And finally, in April, we should have, and that has to be decided by Tunneling Association of India, please. I wanted to say TBD, that means to be determined on that slide. That means that in the last of this training program will be a lecture on life cycle assessment. So sometimes in April, that will be the last one. Okay, we can go to the next slide. And I have once again to ask Mr. Uttam if he can just change a little bit. You know, the slide is here, but it's not. It doesn't fully cover what is on the slide. I have a line. I have a line which does cover some of the reading and maybe last time Mr. Uttam could manage to get rid of that, but this time it came again. Maybe he can do it again. Okay. So the content of the overview of today will be engineering structures in rock, on rock, and off rock. Everything we can talk about engineering structures on rock. Then it will include some physical properties of intact rock, as it has been introduced by the general already, that there is a difference between rock mass and intact rock and rock behavior, which we also have been talking about in previous lectures on the behavior and responsibilities. Then we will talk about rock mass index and classification systems. You know, it's more easy to talk about classification of soil, but I will talk about that also. But the classification of rock is kind of a more complex material. So then we will talk about rock mass, mechanical properties, and finally on the permeability of rock and permeability of rock mass. Okay, so the next slide. Can I ask Mr. Uttam for the next slide? Okay. Well, as an introduction, you know, I would like to explain geotechnical engineering and mechanics of geotechnical engineering, both for soil and rock and its application. What is included in that? There's included the analysis, it is included the design and the construction, both of slopes and retaining structures and foundations and dams and embankments, roadways, highways, tunnels, and other infrastructure which are either made or supported by soil or rock. There is a quest for more sustainability always and resilience of the environment, which is increasing pertinent. Geotechnical engineers have to be able to affect every project from its early stage, and there they play an important role. The geotechnical field is seeking to improve the visibility and diversity and recognition of this profession, which includes design, supply of special equipment also, managing construction, and evaluating risks. We can go to the next slide, please. The next slide shows you some design methods of both soil and rock. And there's a table, and I think it doesn't make a lot of sense to go through this table. So I would like to ask you to look into that table, as this table is explaining examples from different methods. And in particular, we are talking about empirical methods and closed form analytical methods, as well as numerical methods. So that gives an overview of what the effect of time is, and what the effect of groundwater is, and what the effect from the shape of the tunnel is, and whether it's a mined tunnel, means conventional excavated tunnel, or a tunnel boring machine method tunnel. Okay, can go to the next slide, please. Can go to the next slide. After design methods, we will have more of this year's classification of intact rock. Okay, very, very easy, and very much easy to remember also, that the classification starts with very soft rock, and it goes through soft rock and medium to hard rock, to very hard rock, to extremely hard rock. And what kind of testing is used, and what the range of compressive strengths. We will talk about more on the compressive strengths, in particular of unconfined and uniaxial compressive strengths. And this gives a range of that compressive strengths for these different classified rocks, which starts for the very soft rock with a megapascal strength between 1 and 3, and then it goes up to the very extremely hard rock, which is a compressive strength range beyond 200 megapascal. We can go to the next slide also. The next slide shows the context between intact rock and rock mass properties, where intact rock properties are determined from the laboratory tests with regard to the porosity, with regard to unit weight, with regard to specific gravity, water content, durability, abrasion resistance. You maybe remember the Brazilian tests also, the strength and deformability, and the rock permeability. While the rock mass property are determined in situ. The rock mass property, I cannot see that again. Okay. Mr. Uta, maybe you can delete that, but maybe we just go on. The rock mass property are determined in situ with regard to the properties of discontinuities in regard to the deformability, to the rock mass strengths, and to the rock mass permeability. And the picture, the sketch shows on the side what kind of laboratory tests we should do with when we have intact rock. Next slide, please. So rock performing minerals and the context of that minerals to the properties. We are looking into mineral as such, like orthoclastic feldspar and plagioclastic feldspar and quartz, muscovite and olivine and so on. And we are looking to the hardness according to the Mohs scale, which is for feldspar about 6, and for instance, muscovite, it's only 2.5. Where we look into the fracture behavior, there is a good cleavage at right angles for the orthoclastic feldspar, and for the plagioclastic feldspar, the cleavage is nearly at right angles, very, very much. For instance, for quartz, it is about in the same range also, but the structure is different. For quartz, for instance, we have a hexagonal structure, and for plagioclastic feldspar, we have a triclinic structure showing distinct cleavage lamelles. And for the orthoclastic feldspar, we have monolithic, common occurs as crystals. So we go to the next slide, please. So we are talking right now about the physical properties of intact rock. Why is this physical property so important? First of all, because it's an indicator of rock and of rock mass behavior. These physical properties are used in the classification and in engineering of the geologic conditions. It is to estimate the mechanical properties by empirical relationship. We are using also the stress state and predict a change in strength and deformability during saturation or drying, as well as freeze-thaw processes. Freeze-thaw, where we do have it, and in the northern part of India, we definitely have it. So we have to look into that different behavior of the properties. The responsibility for many rock engineering hazards, such as landslides, collapses due to karstic conditions, subsidence, and so on, all that is very, very important with regard to the properties of the rock. Thank you. And for the next slide, please. Can you switch to the next slide? Yes, the next slide is the slide on different type of rocks, which we have just been talking. What type of rocks? We have igneous rocks, and we have metamorphic rocks, and we have sedimentary rocks. And this slide shows what kind of type of rock we have for igneous, what kind for metamorphic, and what kind of sedimentary rocks. And you can also see in the pictures on the left side and on the right side samples of these type of rocks. Also, there is some indication on the unit weight and on the porosity of that rock, which is quite illustrative. Next slide, please. Hello, next slide. Yes, mechanical properties of rock. We are looking into the safety and into the serviceability of engineering structures, which are depending on the stability of the rock foundation or the rock surrounding environment. The rock properties are important for design of engineering structures, including calculations of bearing capacity. And what kind of these properties are we looking at? As I mentioned before, we are looking primarily on the uniaxial compressive strength or unconfined compression strength, We are looking at the triaxial compressive strengths, which is more related to soil mechanics than to rock mechanics. We do it less in rocks, but more in soils. We are looking to the tensile strengths, which is quite low. I will show you examples of that on one of the following slides. We are looking into the shear strengths, and we are looking into the Young modulus as well as into the Poisson ratio. I will give an explanation of what the importance and what Poisson ratio basically means. We have a lot of influence from Poisson ratios in finite element analysis, which we usually do. Next slide, please. Next slide shows that rock, in particular intact rock, is the subject of three primary types of stress. One is, of course, compressive strengths. The other one is shear strengths. And the next one is tensile strengths. Now, compressive strengths decreases the volume of the rock by forces acting inward and directly opposite to each other, while the shear stress is caused by two equal forces acting on opposite directions. So this is the example of how shear strength is acting. And this is the example of how compressive strength is acting and how tension is acting. Now, tensile forces tend to pull a substance apart by outward acting equal opposing forces. So with that regard, the strength of intact rock depends on component mineral strengths, and this way they are bound together by interlocking or even by cementation. Rock failure is generally a shear failure. For determining the above strength values, the tests are conducted either on intact rock space examples in the laboratory tests or on rock mass in the field. Okay, we can go to the next slide, please. The next slide gives a more detailed information on the uniaxial compressive strengths and then unconfined compression strength. Unconfined compression strength, QU, in short UCS, is a strength under uniaxial load in unconfined state. Unconfined compressive strength of dry rock is standard for defining rock strengths. Unconfined compressive strength of saturated rock is lower than that of dry rock. The slide also gives some examples of unconfined compressive strengths for starting with very strong rock, going through all stages from very strong to moderately strong and so on, until to very soft soil, and give some indication of the unconfined compressive strengths in megapascal for each of these different rock descriptions or soil descriptions. Okay. Then on the right side, you can see a diagram of strength and deformability of igneous rocks according to Deer and Miller from literature in 1966. In 1976, about that, I have been working with Don Deer in the United States on the Washington Metro, just as a side comment or remark. But we can go to the next slide, please. Yeah, the next slide gives according what I just mentioned on Deere and Miller, engineering classification of intact rock in classes from A, B, C, D, E, from very high level of strength to a very low level of strength, whereas the unconfined compressive strength in megapascal for the very high is above 200 or above 220 megapascal, and then it decreases down to the very low level of unconfined compressive strength to about 10% from the very high, or 20. This is an indication of 27.5 megapascal. Okay, we can go to the next slide, please. Slide number 15. Okay. So the triaxial compressive strength is measured when the rock sample is confined. Rock sample or soil sample. The strength increases with an increase in confining stress, and the strength is rarely measured in rocks, but more important for soil. As I had mentioned before also, rock strength greatly increases when it's confined underground. When it's unconfined, then it decreases immediately. And confined triaxial strength is rarely measured in rock. As we all understand, it is more common in soils and more important in soils also. Can go to the next slide, please. Slide number 16, yes. So we all have been learned either in our university days or later in daily practice what the Mohr diagram is and what it means, in particular for rock. The Mohr diagram is a shear stress versus normal stress diagram, and it is used to determine the strength and the failure relationship. Triaxial compression tests are performed on rock samples to determine how the rock will behave under different confining pressures. So the intact rock shows the shear strength at zero normal stress or the cohesion, what is called when there is no normal stress, then what we have is cohesion. Cohesion-less discontinuity is shown in fault zones, and it does not show any shear strength at zero normal stress or no cohesion. If you look to the diagram, you can see on the left side, you can see the sample with the sigma 3 and sigma 1 stresses, vertical and horizontal. And here you also have the Mohr cycle here, sigma 1 and sigma 3. And this is the uniaxial compressive strength. And if we have the triaxial compressive strength, we also can get the failure criteria if we draw the line as a tangent between A and B, and we have the cohesion here. So this shows the indication. This shows the indication of vertical and horizontal stresses. Just let me put on my light in my office. Okay, so this explains the Mohr diagram for rocks, and we can go to the next slide, number 17. Number 17 explains the tensile strength of rock, which is very low. The tensile strength is rarely measured or applied directly. Tensile strength of rock is generally about unconfined compressive strengths between 20 and 8. The sample also shows the so-called Brazilian test. The Brazilian test for rock stability, the tensile strength, is not as significant parameter as the unconfined compressive strength. But it is still done in practical geotechnical baseline report. You always can find indications for the Brazilian tests, and it gives some parameter. Okay. Can go to the next slide, please. Slide number 18. Slide number 18 explains the shear strengths and the peak strengths of rock. The peak strengths of rock on initial shearing declines to residual strengths along the sheared surface. You can see here on the left side the ring shear and the confinement of the sample. The thickness of the sample is D, and the general relationship explains that the unified compressive strength is typically ranges from 6 in strong rock to 2 in soft clay. So the shear strength is particularly important for layered rock. We also have two examples on the right side, two diagrams for shear stress and for shear strength, and the relation between these strength measurements. Next slide, please. Slide number 19. Slide number 19 explains rock mass characterization, which is the subject of this today presentation. The rock mass is a matrix consisting of rock material and rock discontinuities characterized and classified to determine the rock mass characteristics by assigning values to a set of rock parameters. So that makes rock mass and rock mass matrix really challenging, because the rock itself is not that much of determining the condition. It is more determined by the discontinuities. The behavior of intact rock material is determined by continuum mechanics, where rock masses are highly fractured. Fractures control the mechanical response of rock masses, which makes determination of mechanical behavior so difficult, and which makes the determination so much dependent on experience and on specialists or on rock mechanic experts. The simplified classification, which should be capable of dealing with geological and geotechnical uncertainties, has evolved for engineering design. So we need it for engineering design, and we have to simplify it. Systems were based on empirical correlations between rock mass parameters and practical engineering projects, including foundational tunnels, slope stability, and mining conditions. So, so this characterization really has been developed out of practical experiences. And the rock mass classification systems were designed to act as an engineering design measurement and engineering judgment. And this is quoted by Bieniawski, one of the I don't know if I should say historically, because I think he's still around. But he has been a very early pioneer in rock mechanics and in classification and characterization of rock masses. So let's go to the next slide, number 20. Slide number 20 deals with parameters. Slide number 20. Yes, please. Slide number 20. Parameters for rock mass classifications. So the overall behavior of rock mass, both engineering properties of rock material and the fractures, should be derived considering the following parameters. These are significant parameters which are used in classification system, whatever the classification system may be, because we have several classification systems. Now, these parameters relate to the strengths and to the deformability of intact rock. It relates also to the rock quality designation, or RQD, very common, considering the intensity of fracturing in a drill core. We have to make a drill core and then we can make a rock quality designation. The rock fractures parameters are also related to the spacing, to the orientation, to the width of the fractures, to the roughness of the fractures, to the weathering conditions, and so on. But other significant parameters relate to the groundwater and to the groundwater pressure and to the groundwater flow also, as well as to in situ stress and to geological structures, in particular with regard to geological fault zones and folds and the like. So the next slide, please. Slide number 21. With regard to rock mass classifications, we have to look into what kind of rock mass classifications are assisted when we design infrastructure, any kind of infrastructure, underground infrastructure. So the rock load classification evaluates the impact of rock load, for instance, on steel-supported tunnels based on a descriptive classification of rock classes, which has done TRIAXIAL, one of the very early classification in 1946. So we look into the time immediately after the Second World War. TRIAXIAL has been lecturing. He has been a teacher on the Massachusetts Institute of Technology, MIT, in Boston, Massachusetts. And he was the one who did the first classification with regard to what has been common technology at that time in the United States, and that was tunnels which are supported by steel arches. So with that regard, TRIAXIAL has made a classification system. Then about 20 years later, or almost 30 years later, Bieniawski has established the rock mass rating, or RMR system, in order to derive the required support measures for tunnels. The RMR was already viewing into conventional tunneling, what in the ITA we call conventional tunneling or NATM tunneling, in the practical use of a few basic parameters. He has established that RMR system with very few, easy to understand parameters. Later on, very soon later on, the QMR system has been established in Scandinavia. The QMR system was supported or developed together with Nick Barton and Lien and Lundy in 1974. So this system is based on history of projects in Scandinavia, has been called the QMR system with regard to the assignment of 6 parameters which are grouped in 6 quotients. And then we have the GSI, or Geological System Index, which was derived, has derived the rock mass properties by using in situ observations of rock mass conditions with correlations from RMR system Bieniawski, okay, and GSI is utilizing rock mass structure and discontinuity surface quality. And this has been further developed from Bieniawski by Edward Hook in 1994. I've been working with Edward Hook in Turkey in 2005, I believe, 2005, 2006. Okay. Let's talk a little bit about engineering properties and unconfined compressive strengths, or UCS. UCS is known as a uniaxial compressive strength, and this is the maximum stress a rock sample can carry under uniaxial or unconfined compression. It is conducted on a prepared cylindrical rock sample with dimensions of length, which is 2 times the diameter The test is typically performed using strain, not stress, controlled testing. Axial strain, radial strain, and axial force are typically measured during the testing. We have seen that testing apparatus in one of the slides before. Can go to slide number 23. Yes, slide number 23. Next slide is samples of unconfined compressive strengths from the point of view of the classification as ISRM, International Society for Rock Mechanics, has classified in 1978. And rock has been classified between very weak and weak, and then most moderately strong and very strong and extremely strong unconfined compressive strength. And the values are given in that table here. I don't need to repeat that, but it is compared also the ISRM 1978 classification and the Bieniawski 1973 classification. So you can see that it is a little bit more differentiated what Bieniawski has been proposing by ISRM. And then we have the British Tunneling Society BS value also. And we have the African Institute of Engineers. They have published something in 1983 also, I believe. Okay. So we can go to the next slide, slide number 24, please. Rock has a history, yes, but what is the history of it? It is the history of a building material. There are numerous examples of ancient people building into rock. For example, we have temples, Kailasanath temple. We have tombs, for instance, in the Lycian rock tombs. We have also natural excavations in Cappadocia in the center part of Turkey. There are also quarries, quarrying rock for structures and megalithic structures. For instance, the ancient pyramids in Egypt, very famous example, but also Stonehenge in the United Kingdom, and Tiwanaku in the South America. So even today, rock is still used as a building and decorative material. Sometimes only as a facade. So we go to the next slide, slide number 25. We have different types and formation of rocks. In particular, we have intrusive igneous rocks and extrusive igneous rocks. Intrusive igneous rock comes from molten rock, also sometimes called magma, which is then further cooled down and crystallized within the earth. Or extrusive, also molten rock, its origin is called lava. It is cooled and crystallized on the surface of the earth. Common intrusive igneous rocks type is granite, and extrusive igneous rock type is called basalt. So please switch to the next slide. In the more detailed explained, metamorphic rock is formed from other rocks by essentially solid state changes in mineralogy and or in texture as a result of a change in a chemical or physical environment. Different temperature and different pressure has influenced that. The common metamorphic rock types are slate and schist and gneiss. Sedimentary rock is, on the other hand, formed by the process of lithification of sediments, biological materials, and or organic materials. The lithification process includes cementation, recrystallization, compaction, and replacement. And the common sedimentary rock types, as I mentioned before, are shale and sandstone and limestone. Okay. So this is the origin of rocks with regard to metamorphic origin or sedimentary origin. Can go to the next slide, please. Slide number 27 gives us some indication on rock properties. Generally speaking, rocks are strong and stiff, and this is in contrast to soils. There is a considerable overlap between the strengths and the stiffness of different types of rock, whether it's igneous rock, metamorphic and sedimentary of rock, and with regard to the unconfined compressive strengths of rock. Igneous rocks are the strongest rocks. The crystallization of the grains forms a very strong structure. Metamorphic rocks are typically weaker than igneous rocks. We can go to the next slide. The next slide asks the question, what is rock? Rock is a lithified or indurated, hardened crystalline or non-crystalline material composed of minerals and mineral-like matters. Rocks are identified by the mode of formation. Well, the mode of formation, whether it is igneous rock or metamorphic rock or sedimentary rock, and the type of and the percentage of minerals in the rock. Therefore, we do microscopic analysis in our geotechnical laboratories. We can go to the next slide, slide number 28. Slide number 28. A little bit different. Well, we talked about igneous rock. No, 28, yes. What is rock? We talked about that. And now we go to the next slide, number 29, please. Types and formation of rock, intrusive and extrusive rock. We have been talking about crystallization of molten rock and different type of intrusive and extrusive rock, magma and lava cooled down. So we have been touching this issue already. I think that is fine. We can go to the next slide, number 30. Slide number 30 is again a slide talking about metamorphic and sedimentary rock, whereas this is important. Metamorphic rocks are basically formed by solid state changes in the mineralogy and texture as a result of the change of the chemical and the physical environment. The common metamorphic rocks are slate, schist, and gneiss. And sedimentary rock are formed by the process of lithification and the biological materials and or including also organic materials. Lithification includes cementation, recrystallization, compaction, and replacement. And common sedimentary rock are shale, sandstone, and limestone. Next slide, please. 31. I think there was some confusion. 31. I'm trying to follow up. Okay. I think 31, in contrast to soils, rock are strong and stiff. We have been considering that. Also the overlap between strength and stiffness of different rock types. We have been talking about unconfined compressive strengths of igneous rock and metamorphic rock and sedimentary rock. I think we can move on because we have been talking about that already. And we are talking now about the essentials of rock engineering. Engineering properties of intact rock are determined in the laboratory using either cylindrical samples or irregular pieces of rock. Laboratory characterization is performed on intact rock samples. Intact rock samples do not contain discontinuities that will affect the sample strength and stiffness. So that is to be considered in the laboratory testing. We can go on to the next slide, number 33, on rock engineering and mixed rock engineering. Here we can see mixed phase conditions according to a publication by Ed Cording in 1978. That was an example which I have been dealing with at the Washington Metro when I worked with Professor Cording at that time. It shows a TBM-driven tunnel, TBM-driven and segmental line tunnel here. And we have a transition from sand to hard clay. And you can see here that this is a transition where we have in this area here a mixed phase condition. When we are in the hard clay, we are again in conditions which are quite different from the conditions in the sand. There's another example on the right side of the same slide. If you look to the tunnel boring machine here, and we have rock, fissured rock, actually fissured rock, and in the fissured rock we have a shear zone. So when we encounter with the tunnel boring machine into the shear zone, we have changing conditions where the advance into the shear zone or faulted zone is creating quite different conditions. So this type of conditions have to be described in the geotechnical baseline report. If we look to the mixed ground, when we are in sand conditions, and we are moving from sand conditions and some boulders also in sand conditions embedded in the sand, and then we move further on to the rock. So these are all samples of where we have to be prepared from the point of view of the design for this type of four types of different mixed rock conditions. In the last example here, we can see that we move with the tunnel boring machine, either with the tunnel boring machine or with other excavation tools, into conditions from rock into sand. And we also have a groundwater table which is above the crown of the excavation. So all this is mixed rock engineering, which we have to think about and be prepared for in our design. Next slide, please. Slide number 34. Slide number 34. Should be the slide, rock mass versus intact rock. Yes, rock mass versus intact rock, where the rock appears in nature as a rock mass, basically. And you can see here this very illustrative picture. The rock mass is divided into blocks by discontinuities. rock mass properties are controlled by this type of discontinuities. For instance, bedding planes, joints, faults, and so on. The intact rock samples are obtained from within rock blocks by coring operations. The intact rock is typically stronger and stiffer than the rock mass from which it was obtained when it is unconfined. Anyway, so this is always something which makes it a big difference, very important difference from the rock mass and from the intact rock. So let's go to the next slide, number 35. So slide number 35 shows classification systems, different or an overview of principal systems of rock classifications. This has been published by a Japanese engineer by the name of Tatiya in 2005 on civil excavations and tunneling. Classification systems, the first one on this table here is the classification according to TRIAXIAL on classification of rock loads, in particular for tunneling with steel support. And then we have rock quality designation of the RQD. So we have been talking about this also, but this gives you maybe a better overview of different classification systems. In this case, we are talking about RQD. RQD, according to Bieniawski, and we have classification very easy, very simple, between excellent RQD values between 90 and 100, good, fair, poor, and very poor conditions, where very poor conditions are lower than 25 percentage in the RQD classification system. Then we have rock structure rating, RSR, which has been developed by Wickham, and basically talking about Wickham with regard to geologic and construction permeation. Then we have RMR system, rock mass rating system from Bieniawski, and we can see that this system is also used in mining and in tunnel engineering also, with uniaxial compressive strengths and different values in the uniaxial compressive strengths. Okay, so this table, I would recommend you take it a little bit more into detail. I think it makes no sense to talk about more on that table, because it has to be considered separately. Let's go to the next slide, slide number 35. Slide number 35 is the slide on the design process of rock. According to the ITA, International Tunneling Underground Space Association, we can see here when we start the design for a project which deals with rock, we have to, first of all, we have to go into site investigation in order to get a clear picture of the geology. And after we have a good picture of the geology, we go into geotechnical investigation in order to make the ground characteristics. And from there on, we go with our information and experience to go to the best, make the best choice for the excavation method, and we relate the excavation method to the structural elements which we are using, either cast in place concrete or shotcrete or precast concrete segments and so on. Then we go from there in the design to the mechanical model, to the statical system or structural system and statical analysis. And then we go from there to the safety concept and to possible failure hypothesis, which is a criteria in the design. And from that criteria, we continue to either yes or no. And sorry, I still cannot see because it's overblended. What is the next? But you may see what is the next step. If it's no, we have to go back to the excavation method, make a re-evaluation of the excavation method and of the structural analysis and of the design criteria. So finally, we are coming to the detailed design and from the detailed design to the contract documents. Okay, so let's go to the next slide. Still, I cannot see, Mr. Uttam, I cannot see what is on the slide because it's covered. If you can uncover, would be very good. Otherwise, we go to the next slide, please. I don't know what you can do. Hang up or go to the next slide, slide number 38. Can you go to slide number 38? Slide number 38 is the slide on stress-strain relations for some rocks. You can see the type of rocks I cannot see, but you can see the types of rocks here, which is in the diagram between the applied stress and the strain. And we have different dry and confined conditions, which are more ductile failures when it is confined. And then we have typical brittle rock failure. And then we have residual strength indication here. And the development of the unconfined compressive strengths with regard to the yielding point and the peak strength and the residual strength. So I don't know what I can do because I still cannot see the full slide. It's all covered. The lower part of the slide is covered. I cannot see. Okay, so we have reached slide number 39. Slide number 39. gives an explanation on the deformability properties of rock, in particular with regard to the modulus of elasticity, or Young's modulus, and with regards to the stress-strain diagram, which refers to the recoverable elastic deformation. The non-recoverable part is termed plastic deformation. Okay, so commonly the elastic deformation is directly proportional to the stress state of the sample. The unconfined compression is the product of elastic or elasticity. E modulus, the E modulus is the relation between sigma and epsilon, or the elastic plastic and the nonlinear elastic state. So the proper value of the modulus is the one which is best related to the strain level and confinement level of the rock under the load. The accepted practice in rock engineering is to use the tangent modulus at 50% maximum load. So you can see here the loading and unloading of different models of material. This is a linear elastic material, this is a plastic material, and this is a brittle material which is damaged due to the formation of microcracks during loading. Microcracks are closed upon removal of the load. In the picture you should see, I cannot see that, but in the picture you should see some of the samples which have been used in order to determine this type of diagrams. Okay, so the next slide, we have seen that deformability. The next slide is the Young modulus of elasticity, or elastic modulus. There are different values for elasticity, for metamorphic rock, and for sedimentary rock. You can see here, this is the metamorphic rock conditions for different classifications. We have very low strengths, and we have very high strengths here. And here we have the Young modulus of elasticity. Same here. We have also, the rock is different. The rock is sedimentary rock, and the different types of classification here. Different types, A, B, C, D, E, very low strengths and very high strengths. And these values for the comparison between sedimentary rocks and metamorphic rocks. We can go to the next slide, please. The next slide is talking about the Poisson ratio, which is also a very important rock property. Poisson ratio is mechanical property involved with relating the lateral strain to the longitudinal strain. It is usually used in numerical stress analysis for the unconfined compression strengths test. The Poisson ratio is the ratio of the lateral extension expressed as a fraction of the longitudinal strain. So this is an interesting value, very important. It has significant influence on the deformability, on the deformation behavior, on the stability of the rock. And you can see here on this slide different types of rock. We have andesite and basalt, and we have different types of dolomite and gneiss and granite and so on. And on the left side, you can see how the Poisson ratio is defined. It's defined as the quotient of the lateral strain and the longitudinal strain. And it's usually typically range between 0.1 and 0.5, where the Poisson ratio varies depending on the direction of the loading. So we have now I can see the picture. Now again I cannot see. Now it's already covered, but for a moment I could see it. I don't know if you can manage to do this again, then I can see the picture better. Can you do it again? If not, it's okay also. Okay, so that was the Poisson ratio for different types of rocks. We can go to the next slide, please. The next slide gives us the physical and mechanical properties of unweathered rock. Unweathered rock. So the rock types are listed up here, starting with granite, sandstone, different types of sandstone, limestone, shale, and so on. And the parameters which are shown here are density, dry density, porosity, dry unconfined compressive strength, and mean unconfined compressive strength in megapascal, and unconfined saturated compressive strength, modulus of elasticity, strength, and angle of internal friction also, cohesion. So these are different types of, different values for different types of rock on this slide for your orientation, in order that you can get some indications of what is shown or what is used in the design of underground infrastructure. You can go to the next slide, please. Slide number 43. Slide number 43 should be another classification. Ah, now I have the full picture again. Very good. Now not. Now it disappeared again. I don't know what happens that it disappears, but now I have it full picture again. No, disappeared again. I don't know whether you can make it. I don't know how. Anyway, you seem to be in the right direction to give me the full picture of the slide on my computer. There should be one or two more slides. Classification of the Korean granite. You know, the Korean granite, very well investigated rock, with the type of grade from 1 to 6, from completely fresh rock to slightly weathered rock, moderately weathered, highly weathered, complete weathered, and residual soil, also residual soil. And then we have the description very brief description, very precise, no fine fracturing, microfissures spaced at 1 centimeter, microfissures spaced between 5 and 10 millimeters, and so on. So the more we are getting softer, the more the description takes care of that. And then we have indications for field moisture in percentages, and for unconfined compressive strength in dry and unconfined compressive strength in saturated conditions. All, yes, now it's covered again, but for a moment I could see it. Okay. So something is maybe improving towards the end of this lecture today. Anyway, we have quite high numbers for unconfined compressive strength in dry conditions, in saturated conditions, and completely lost also by saturation for completely weathered condition. Okay, so that is a table which gives you orientation in your future projects, and will help you to better understand the geotechnical behavior. The next slide, I'm not sure if it's the last one or if there's one more. Now I can see my picture on my laptop again, full. Okay, now it's disappeared again. This slide, anyway, one of the last slides is giving an indication of main features occurring in rock mass. So we have rock material, and we have discontinuities, and we have description from the rock type with regard to minerals, texture, and composition. This gives us the rock type and the name, and the condition with regard to anisotropy or weathering condition, alteration condition, and strike and dip condition of the foliation in the bedding. So these rock material properties will be entered into the rock mass definition for the detailed jointing of the rock characteristics, the rock properties, the joint characteristics, the degree of jointing, the pattern of jointing, and the orientation. And from the point of view of discontinuities, we are giving a description of the joints with regard to breaks, break behavior, and fractures, with regard to waviness, smoothness, length and size, and joint wall condition, spacing, and orientation. We also give an indication on the singularities and on the fault zones, and all these information will be entered into the description of the weakness zone, the size of the zone, the type of the zone, the filling material, and the orientation. And finally, I want to again quote a statement from Professor Terzaghi with regard to that rock material and discontinuities. Since joints are among the most important causes of excessive overbreak and of trouble with water, they always deserve careful consideration. Yes, Professor Terzaghi is 100% right. We have to have a very specific look, and we have to also define soil and rock material, and as rock material, rock mass, and discontinuities are determining the conditions, whatever we have to consider in the design. So there may be another last slide. Yes, the last slide is the slide on the discontinuity size in rock mass. And this slide gives a very good overview of the difference in size between different types of discontinuities, according to Palmström in 2001. So it gives a description of the rock defects and of the joints and of the weakness zones also. And the rock defects, which are expressed in micro cracks in the range of 0.01 meters, and also the joints in the range of 0.1 to 10 meter distance, and of the fissures and bedding planes and seams, and of the fault zones. And here we have already in the fault zones those weakness zones, which give an indication of the length of such areas, the length which can start from 10 to 10,000 even. So that is the engineering property of a rock mass, often depend on more on the system of geological defects within the rock mass than on the strength of the rock itself. So basically, this is a confirmation. Yes, now this is the last picture, and now I get the full picture on my computer screen. So thank you very much. You have done a great job in solving this problem. It was really appreciated. So with that last slide, number 45, which is a confirmation of the two very different experts, Terzaghi and Palmström, different also in regard to the quotation of their statements between 1943 and 2002. So there are 60 years in between, but it is all basically confirming what the importance of geotechnical characterization relates to. And I think that if I could give you some information today to your future handling of rock engineering and rock design in underground construction, then I think that we have achieved what we wanted to achieve today. But as we still have a little bit of time, I would be very glad and I would be very honored if you have some more questions. So please let me know your questions either right now, or if you write down your questions and you send it through Tunneling Association of India or through the Central Board of Irrigation and Power. I will be happy to respond in writing also. So for that moment, I appreciate it to have this lecture at the end of the year almost, which was quite a difficult year, but as engineers, we could show that we can master difficulties by inventing new solutions, new processes, innovative communication system, and I think it has been really great to be with you today. So I would like to thank all of you for your attention, and I appreciate if you have further questions. Thank you.
Thank you, Dr. Harald. May I request to all the participants for any questions, query? Participants may ask the questions if they have any.
If there is no question, then I would like to make a final remark. You know, this geodetic characterization is a highly theoretical topic, and it's a highly important topic also. But as it is a highly theoretical topic, it needs to be studied. Maybe that 2 hours of lecture is not enough. But if you have a concrete project, and if you would like today or in the future to have answers to some specific questions with regard to soil or rock properties, please do not hesitate to send me these questions, and make a little sketch of the project, very brief description of what the project is like, so that I can understand the project very well and give you a competent answer to your question. That would be very beneficial, and I think that India has such a great opportunity going underground with infrastructures in so many aspects, in transportation, in energy, in hydropower, in different types of even building material use. So I think it would be very good if we can keep in touch with in that regard, and we can exchange information also.
Thank you, Dr.
Hello.
Harald.
I have a question.
Yes, please.
Yeah, like we classify the rocks as high strength, low strength. Can we classify the rocks based on like weathered rock and hard rock? A clear criteria to classify the rock as weathered rock and some rocks as hard rock.
Well, I would like to refer to the classification systems which I did show in the slides. You know, so to classify, we have different classification systems. We have the very simple classification system of Terzaghi, where Terzaghi is related, is basically base his classification on steel support, which has been used in the United States for a very long time. I remember that when I started to work with Washington Metro, they still had the big station, underground station and mine station. They still did use the steel support system from Terzaghi. And I was starting in the United States, in Washington, in 1985, 86 or so. And they slowly changed with regard to the classification from Terzaghi to Bieniawski, and from Bieniawski to ISRM. And then these different excavation technologies, they had a big impact on the classification also. So nowadays you cannot find except in very remote areas, maybe in some of the former Soviet Union states, that you can still find classification for regard steel arch support, but usually you don't find it anymore. So the classification is related to Bieniaszki, to Witthorn, to different classification system. And the RNR or RQD classification gives you the criteria for the classification. So, for instance, the classification, the Scandinavian classification of Barton is using 6 parameters, and these 6 parameters are again combined into 3 simple parameters, so you can make a classification according to RQD or RMR. So the classification according to that is not a problem. What the problem really is later, that when you start with the excavation and you have to make the verification of the classification, the verification of the classification in the design or in the specifications, and in the real nature at the tunnel face. So there is where the conflict may start. You know, that they say, the contractor may say, you have classified RMR number 5, and it is not RMR number 5, it's only number 4, because this factor or this quotient has been different from the point of view of rock property. But the classification, as soon as you start with the classification and you make a decision what kind of classification you are using, you are fine. This is all perfectly working. Only when it later comes to the conflict at the tunnel phase, in the construction, at the excavation, then there may be a conflict and a dispute.
Okay, thank you.
Sir, I have a question.
Yes, please.
Can I ask?
Yes, please. Yeah, I cannot see you, but you are happy to ask.
Sir, I want to know that what's the exact way to calculate SRF for calculating that Q value in rock mass classification? SRF, stress reduction factor.
SRF.
Yes, sir.
I'm not sure that I have mentioned SRF in my presentation today.
Oh, okay, sir. Okay. Talking about the Q system, so there is one.
Let me answer your question in writing.
Okay, sir.
So can I write down SRF criteria?
Yes, yes.
In classification?
Yes, sir.
I will give you an answer in writing, okay?
Okay, sir.
And I will send the answer to Mr. Sunil Sharma. Is that okay? Because, or you can give me your email address also.
Oh, okay, sir. Okay, sir.
What is your email address? I cannot hear you anymore now. Can you give me your email address?
So we may forward the answer to them directly.
Yeah, but I need something. I need the name of the questionnaire.
My name is Anshul Gumasta.
Again,
Anshul.
can you slowly speak, please?
My name is Anshul Gumasta, sir. ANSHUL. Anshul.
ANSHUL.
UL, Anshul.
UL, Anshul, yes.
Yes, Gumasta, Gumasta, Gumasta.
Gumesta. Gumest. Correct? Mr. Anshul Gumesta.
Gumasta.
Tasta.
Correct.
Gumesta. Okay.
Any other questions, please?
Yes, the question is the influence of SRF in classification. Is that correct?
Mr. Anshul, can you please reconfirm?
Mr. Anshul, I will. Hello.
Sorry, sir, I was out of network, so I couldn't.
Can you please reconfirm your questions?
Can I?
Yes. The question is the influence of SRF in classification.
No, sir. Actually, my question is, what's the exact way to calculate SRF for Q value calculations? SRF. Stress. What should be the exact way to calculate SRF in value calculation?
How to calculate SRF?
Yes.
Okay. I will give you an answer. Very good question.
Thank you so much, sir.
Pardon me?
Any other question, please?
Yes. The question I would like to repeat. The question is how to calculate SRF in the classification. Correct?
Yes, sir. Yes, sir. Absolutely.
Okay.
Thank you, sir.
You will get the answer. I will immediately try to give you an answer. Okay. Very good. So do you have a specific project in mind, or is it just a general question?
No, sir. It's not general. I am working in Arun 3 hydro project in Nepal from SJVN. It's a public sector undertaking in India. So I am working in a project, and in field I've shown. I've been through this type of problems to calculate SRF for calculating Q value for rock mass classification.
Okay. So what is the name of the project in Nepal?
The project name is Arun 3 hydroelectric project, sir. It's a 900 megawatt project located in Sankho Sabha district of Nepal. And
it's in the west of Nepal.
Yes, sir. It's eastern Nepal. It's extreme east of Nepal.
In the east
yes,
of
sir.
Nepal.
Yes.
So it's in the direction to Bhutan.
Yes, sir. Definitely.
And the name is Arun.
Arun 3 hydroelectric projects. Actually, it's the third project in Arun River, sir, located on east of Nepal.
Yeah, I have been involved in Nepal in the Upper Kanali and in the Melamchi project, and you know this project. Nepal has a number of hydroelectric projects now.
Actually, I'm new in Nepal. It's been 2 years I am working here. So I am working here from a company named SJVN, Satluj Jal Vidyut Nigam. It's a pub.
Rampur is an SJVNL project.
Our project.
Yes, that's right. Dr.
I have been working on Rampur for a long time.
Yes, sir.
Yes, sir.
Yes.
Dr. Wagner, I'll give you a little background. Usually what happened because of SRF, the Q value gets influenced and then the rock classification gets changed, whether it is rock mass in class 3 or class 4. And
Yes.
fortunately, then the dispute between the contractor and the client, it arises. The gentleman, Mr. Anshul, is from the client side. So mostly that's why
Yes.
he just wants to understand that in what way he can make it more logical and scientific to show that SRF is whatever is worked out is correct or it has authentication. Because mostly both the parties have dispute and then because the rate for the excavation of the rock mass is determined by rock mass classification.
Okay, I understand. Yeah. Therefore, I think it's a very important question, and let me give you a good answer. I will work on that very soon.
Okay, sir. Thank you, sir. Thank you so much
Okay.
for this.
There any more questions?
Any questions further from any of the participants? May I request to the rest of the participants if they have any questions, query, they may ask. I guess no. So I think we should conclude it. I express my sincere gratitude to all for participating in today's virtual training session on geotechnical characterization. I would like to convey my special thanks to our senior Vice President, former Lieutenant General Suresh Sharma, and Vice President Shri D.K. Sharma. I'm very thankful to Dr. Harald Wagner for sparing his valuable time for conducting today's virtual training program. I'm sure all the participants will be benefited from his vast knowledge shared during the program. Thank you so much. Stay safe, stay healthy. Thank you. Thank you all.
Thank you very much, and I wish you all a prosperous, a healthy, and a good New Year.
Thank you, sir.
Dr. Wagner, thank you very much for taking time out and benefiting my colleagues and youngsters in India. And it was very useful from Indian perspective. And I take this opportunity to wish you Merry Christmas, Happy New Year, and very happy festival season. Enjoy yourself and be safe.
Thank you very much. Merry Christmas and Happy New Year also to everybody in Tunneling Association of India. Thank you very much.
Thank you.
Thank you, sir. हेलो हाँ जी हाँ हाँ ये स्पॉन्सरशिप वाला अच्छा सर को मैं बोलती हूँ फिर ये तो अभी नीचे किसी मीटिंग में बैठे हुए हैं मैं अभी बोल के सर आपको अपडेट देती हूँ ठीक है बिल्कुल